Dear sir and madam, as well as my respected audiences, let me introduce myself. My name is Amsalut Tasamma. Now I am going to present my research paper entitled as Automatic Quality Attribute Scenarios Identification and Generation from Quality Attribute Requirement in a Machine Learning Approach. Here are some contents, but in order to keep my time, I am going to start in the introduction part. So when it comes to the introduction part, software architecture plays a great role in bridging the gap between business goals defined by the stakeholders as well as the final software systems. So stakeholders can be considered as quality attribute requirements. So good software architecture makes the system easy to understand, change, test, and maintain. So quality attribute, also called non-functional requirements, assists software test engineers and end users to evaluate the performance of the software quality and to develop a good software architecture design. So detecting and analyzing quality attribute scenarios in early development stages provides reduces risks, improves the developers' understanding, and in order to assist the software architects in order to evaluate the software architecture. So availability, usability, testability, modifiability, security are some of the examples of quality attributes. To describe a tangible quality attributes, first we have to start to write a quality attribute scenarios, also called QAS. So in software engineering technique, use case describes what functions the user wants to be implemented. Quality attribute scenarios describes how the function performs within the design application instead of functional requirements. So quality attribute scenarios assists in the specification of quality attribute requirements and design qualities. So it consists of 6 components or elements, which are the first one is source of stimulus. Source of stimulus means it is an internal or external entity which could be a human or a machine or a computer system or any other actuator that capable of creating of a stimulus. That there is a stimulus. A stimulus means a condition that requires an answer when it is notified by the system. And the other is artifact, which means it is one that obtains the stimulus. It can be a component of the system, the whole system, or several systems. And the fourth one is environment, which means environment is describes the situation or the system or the degraded either the degraded system or when the stimulus occurs. For instance, the system might be running in normal or in degraded or normal or overloaded situations in heavy traffic, or in running in normal or overloaded situations in heavy traffic and others in other status. So system needs to respond to the external stimulus. The other is response. Response, which is refers to a response of the artifact to the stimulus. And the last but not the least is response measure. Response measure refers to the measure that should be tested for response to evaluate if the requirements are well implemented. So it is some measurable function is known as response measure. So let us take as an example a developer wishes to change a graphical user interface to make a screen background color blue. This change will be made to code at the design time. It will take less than 5 hours to make and test the change, and no side effect change will occur in the behavior. So first we have to determine what type of the scenarios can be described. So the type of scenario can be identified as modifiability scenario. So let us start the generation or the extraction module. For instance, source of stimulus. So in this part of scenario, the stimulus element of the scenario determines who makes the change: the creator, the system administrator, the developer, the end user. So that is the developer is the source of a stimulus. The other is a stimulus. In this part of scenario also we have to understand that the stimulus portion of specifies the change to be made and defined in the stimulus sections, the addition of the function, the alteration, or the existing function. So the stimulus indicates that wishes to change or wishes to alter the graphical user interface. So stimulus is wishes to change the graphical user interface. The other is artifact. So when to consider the artifact, it defines what is to be modified in this section of the scenario, which is the functionality of the device, the platform, the user interface, the environment, or what is. So the user interface is the artifact part. The other is the environment, the component of the scenario that determines once the change can be made in what, in design time, in compile time, in runtime, or what. So at design time is the environment can be considered. So when when come to the response, in this part of the scenario, the change must understand how to make it as well as and then make it, test it, and deploy it. So the response indicates that the change made with no side effects. The other is the response measure, which is some measurable functions, or the potential response in this section requires the time or the iteration or the expense time and cost of the most. So it takes the time. So 5 hours is the response measure. The response measure. Okay, the other is the statement of the problem. So nowadays most of the researchers have devoted their time to address different researches to address software architecture, software testing, and UML diagram model understanding. So addressing the problem of quality attributes understanding in the software architecture allows a computer to perform tasks that require semantic understanding without the intervention of the person. So in the existing traditional approach, generation of quality attributes can be carried out based on 6 quality attribute elements or 6 quality attribute components, as we have to be presented in the earlier. So identifying and generating of quality attribute scenarios in a traditional approach is very challenging and complex task that requires much time, and it requires a high amount of budgets and energy, and error-prone tasks, especially for novice or inexperienced users. So it is also an error-prone task to dig out the critical quality attribute scenarios components, especially for the inexperienced users. This identification and generation of appropriate quality attribute scenarios parts automatically are a crucial, or it is very important for documenting and design of good software architecture qualities, and to evaluate or to measure the testability and the non-testability quality attribute scenarios. So in order to address these research, just we have to design 4 research questions. So the first research question is how to characterize quality attribute requirements for automatic quality attribute generation, and the other is how to develop a model that helps in extracting the 6 parts of quality attributes automatically from quality attribute requirements. The third is which machine learning algorithm work best for quality attribute scenarios identification model, and the last but not the least is to what extent does our model works in identifying and generating the 6 parts of quality attribute scenarios. So the general objective of our study is to develop an automatic quality attribute scenarios identification and generation model from quality attribute requirements using a machine learning approach. So in order to address this general objective, to characterize, there are some specific objectives. The other is, so the first one is to characterize quality attribute requirements for automatic quality attribute generation, to prepare quality attribute scenarios dataset, to develop an identification and generation model, to evaluate the performance of proposed model within the prepared datasets, and to compare best machine learning algorithms for developing quality attribute scenarios model and identification models. So here are some of the significance are to save time and cost as well as reduce error prone to while generating the quality attribute scenarios is traditional, so it takes much time. So based on our model, that is it reduces the time as well as reduce the budget. So the other is to increase better understanding for architects and stakeholders in evaluating and the design of good software architecture design perspectives, and improving architectures to generate relevant quality attribute scenarios components that helps the design quality in software architecture, assists for software architectures in better understanding and reasoning about why the architectural decision rather than focusing solely in the solution. So significant for help in the improvement of architectural decisions and design qualities are some of the significance of our study. So in order to show the related works, the first one is Gilson and Galster proposed a machine learning approach to identify quality attribute scenarios, quality attributes as defined in quality models. So in this part of to validate their approaches, the authors use an openly accessible 1,675 user storage datasets, but they didn't include conducting studies with architects to see the quality attributes identified from user stories, confirming the quality attributes quality architects had already thought of, as well as they didn't consider and their model cannot be classified compound and complex sentences. So the model they have to be proposed only identify the simple sentences only. The other is Sevomri, Inchala, and Fati proposed a model for generating a use case diagram from users requirements document using a post tagging approach. So they attempted to generate actors and use case using a probabilistic classification model along with minimal support from the rule-based methods. The challenge here related to non-functional requirements or quality attributes are to incorporate, include, and extend features for the use case diagrams and other diagram perspectives. So when come to the quality attribute scenarios identification and generation model, which is our methodology, so here are some of the proposed models, identification and generation models. So in this model there are 4 parts. The first part is text processing part. So in text processing part, some of the NLP or natural language processing parts are applied. For instance, when to first we have to prepare the data sets. So after we have to prepare the data set, we have to tokenize and we have to remove the stop words in order to removing unnecessary words that may hurt the model production, and for normalizing our data sets, as well as stemming to find the root words that may predict work best for our algorithms. So after we have to text pre-process, just we have to feature extraction. So in order to feature extraction, we have to we use TF-IDF text vectorizers have been used since it is the reason why we have to choose TF-IDF vectorizer is it is very important for improving the recall and the precision, as I have stated in our article review paper. And after we have to vectorize our paper, just we have to design a model, a machine learning model. That is, we have to design a model based on 6 traditional algorithms, that is support vector machine, KNN or K-nearest neighbor, and naive Bayes, and logistic regression, and scholastic gradient descent algorithms. So based on these 5 algorithms, we have to design our model. So we have to train and testing approaches. So after we have to train and test, just we have to identify the type of quality attribute scenarios. Is it testability? Is it quality attribute availability? Or is it quality attribute security or testability? So after we have to identify the quality attribute scenarios, just we have to build another model, which is a custom named entity recognition model, that is named entity recognition model. So we have to design model, and we have to manually labeling and tagging and training, validation, testing. So finally, the 6 quality attribute scenarios, also called source of stimulus, artifact, environment, response, and response measure, can be extracted entities. So when it comes to the generation module, this part of the module is the main component of our relevant elements generation or component extraction module. So for instance, here is the system, in this system, and here are the quality attributes, and it is specific of quality attribute scenarios. And quality attribute scenarios can be also classified as general quality attribute scenarios and concrete quality attribute scenarios. And concrete quality attribute scenarios can be characterized as concrete source of stimulus, concrete environment, concrete artifact, concrete response, and concrete response measure. And finally, we have to extract the module. So the quality attributes parts of the modifiability illustration have been characterized as, for instance, here is the modifiability. Let us take as an example the modifiability quality attribute scenarios. And after quality attributes, it can be characterized as quality attribute scenarios, and quality attribute scenarios can be characterized as concrete quality attribute scenarios, and concrete quality attribute scenarios can be characterized as concrete source. Concrete source can be developer can be considered as concrete source, and add, delete, modify, functionality changes can be considered as concrete source of stimulus, and build time, design time, compile time can be considered as concrete concrete environment, and persistent storage, database repository or system can be considered as a concrete artifact. Deploys modification can be considered as concrete response, and time in delay or cost in budget can be also considered as concrete response measure. So this component in the main unit of the quality attribute generation model, so used to identify the 6 quality attribute elements or components, as I have mentioned in earlier. So custom named entity recognition model can be designed like this way. And first we have to quality attribute scenarios dataset. So after quality attribute dataset, we have to text pre-processing by manually annotated data, labeling and tagging. So after we have to tag the data, just we have to train, validate and testing data, and after we have to create and train, validate and testing. Just the final result would be extracted like these 6 quality attributes elements or components. So quality attribute scenarios entity recognition, we use the 6 quality attribute elements identification definition, and we manually labeled and assign each tagging entities. So the relevant elements selection can be used. For instance, a remote sensor input arrives every second during normal operation of the system. So the service of the sensor status determined within 250 meters per second after receiving the sensor input. So in order to relevant or in order to manually annotate our dataset, just response remote sensor is an actor or it is unactivated, that is, so that can be extracted or selected or manually annotated as source of stimulus, and input arrives, it is a stimulus, so it can be characterized as a stimulus, and that is normal operation, degraded operation, normal mode or degraded mode or overloaded mode. It is one part of the environment, so it can be normal operation can be characterized as environment, and the other is system percent storage database and user interface. So that is an example of system. System can be characterized as system. The other is status determined, it is the final result. So after stimulating some actions, the final response should be status determined, status deployed or blocked. So this is response can be characterized as status determined can be characterized as response, and finally the response measure as that maybe the time or the budget. So 250 meters per second can be characterized as response measure. So after we have to manually annotate our dataset, just we have to prepare some experimental research approach and result and discussions. So data collection and preparation is the first stage of our research. So since there is no ready-made or there is no datasets, quality attribution dataset, so the experimentation is beginning with preparing quality attribute scenarios. So the quality attribute scenarios might be as I have compared or as I have gathered from different article reviews and quality attribute scenarios or non-functional requirements or software architecture books and architectures. So after we have to prepare, just we have to manually annotate data, and we have to used research questionnaire method in order to manually annotate by domain experts. So after we have to annotate the data to evaluate the quality attribute scenarios classification model, first manually annotated documents have created, and dataset preparation. So here are some of the dataset preparation as I have. So we have to manually we have to gather our datasets for performance 191 datasets, and for availability 156, and for modifiability 173, and for security 196, and for testability 175. So the total 891 datasets can be acquisited and can be manually annotated. So after we have to gather and we have to manually annotate our datasets. So we have used classification and identification model. So in order to identify the type of quality attribute scenarios, so we used evaluation metrics to train and test the performance of our proposed models. Confusion matrix with accuracy, precision, recall, F1 score are some of the metrics of our model. So we selected those evaluation metrics because the size of the data is in imbalance. So confusion matrix is mandatory to evaluate the performance of the system. For evaluation model, we have splitting the dataset IT by 20 training and testing respectively. So after we have to train test split, here are some of the train test split. Here are the training data, and here are the testing data. So I mean here are the testing data, which means from the dataset here are correctly predicted our datasets prediction results for the testing data or the identification For instance, from here are the KNN. From the KNN, here is the KNN. So it's predictably correctly identified 164, correctly identified, and incorrectly identified 15. The other is SCVM. Here is 175 testing data can be correctly identified, and only 4 data can be incorrectly identified. The other is naive Bayes. From the naive Bayes, 159 tests can be correctly identified, and 20 testing data can be incorrectly identified. And the same as SCVM, stochastic gradient descent or SGD can be correctly identified as 175 testing data, and 4 testing data can be correctly identified. So here are the results. So experimental evaluation results for the CNR, which is the generation model, that is the previous one is the identification model. So the CNR model or the custom named recognition model is, first we have to select the size of the data. So large models tends to perform better, but requires more data and more time to train efficiently. So we select the medium NCore WebMD-SPACY model for model in the loop data collection. Amount of training data, we manually label a set of scenarios selected random from quality attribute scenarios for testing data. So we trained a custom named entity recognition model in SPACY for detecting it is for quality attribute scenarios components. Finally, we used testing data to evaluate the results of training the SPACY medium English model. So we conducted the custom named entity recognition experiments performance model. So in order to evaluate the custom named entity recognition model, we used precision recall and F1 score metrics. So the model achieves 92.3%, 93.3%, and 92.8% for precision recall and F1 measure respectively. And in order to show individually, for instance, source of stimulus, 90% precision, 91% precision, and 91.1% F1 score, and stimulus 91.3 precision, 92% recall, and 91.5 F1 score. And for artifact also that is high prediction, 96.7, 98.3, and 97.7. But whereas the response measure is 95.6. I mean the response is 80.3 and 80.5, which is low when compared to the environment and the artifact. This is due to the data similarity, as well as most of the time the environment and the artifact is less data short, but the response is large segments. So due to that, the response can be predicted. Our predictions, and here are the contents. So NFRs or quality attributes are requirements that determines the characteristics as a software system exhibits when it in the conclusion, non-functional requirements or quality attributes are requirements that determine the characteristics of software systems exhibits when it provides services to end users. In the requirement listation and analysis phase, little attention is given to explicitly identified and document quality attributes. As we have observed from the overall experiment results shown earlier, we have compared machine learning algorithms, 5 machine learning algorithms. So those 5 machine learning algorithms are KNN, SCVM, logistic regression, stochastic gradient descent, and naive Bayes algorithms for classification or identification of quality attribute scenarios. So the proposed model achieves quality attribute identification accuracy for SCVM and SGD at 97.7% accuracy, which is better, and the others logistic regression, which is 96% prediction, and 91.6 and 88.8% is predicted at KNN and naive Bayes respectively. So after we have to identify the quality attribute scenarios, we developed a new custom named entity recognition model to generate quality attribute scenarios components or to extraction the 6 elements. So we used the precision recall and F1 score metrics to evaluate the CNR model or the custom named entity recognition model. So the model achieves average 92.3% precision, 93.3% recall, and 92.8% F1 scores. So in general, we believe that our proposed model was relatively well performed under a variety of some constraints. So the contribution, here are some of the contributions. So we have prepared equality attribute scenarios dataset, which can be initial point that might help for the new researchers to study further, and that is, it is already the ready-made dataset. So that is our contribution. And the other is we have to produce a model to identify quality attribute scenarios identification and generation model that might help the software architectures, the end users, and the software testers in order to evaluate the software quality and to design software quality architecture, and to identify the testability and non-testability quality attribute scenarios. And we have evaluated the model using the data produced for this purpose. So as a future work, our proposed model was tested with a small amount of corpus, which is 891 datasets, which is very small. So the next researcher might add an match datasets, and based on these datasets, and they used deep learning. So based on deep learning techniques, they might improve our dataset. So thank you very much. Thank you.